This video is about multiplication, and it is meant to go with the handout entitled Connecting the Area Model to the Break-Apart Method to the Traditional Algorithm. So this is on Moodle. Directly above the link to this video, it says print, and that's the link. I have it both as a Word and as a PDF. So the first question is, do you have your handout? If so, get it, sit it next to you, and let's go through it together. You probably are going to want to make some notes on it, make it make a little bit more sense to you. This video is meant to complement that handout. They go together. Neither one of them, in my opinion, has enough information to stand alone. If you don't have that printed out yet, please pause this video. Please wait to watch it until you do have it printed out. This video is going to feel a little confusing and a little fast and a bit incomplete if you don't have those notes. So again, print out those notes is my recommendation. You can print them out on campus, local library, or if you have your own printer, but print it out before you watch this video, please. Okay, so let's look at page 1. So we're connecting the area model to the break-apart method to the traditional algorithm. Now, you don't necessarily have to know what any of those things are, but those are the things we're going to be talking about within this particular model. So, whole number example. So this is 12 times 26. So we've already talked about the area model in the visual representations. So we're just building on that. So this is 12 times 26. So if you notice, right, there are 12 across the top and there are 26 down the side. It's a lot to count and draw out. But remember, multiplication can be interpreted as repeated addition. So I'm adding 12, 1, 2, 3, 4. Hopefully you get the idea. And I do that 26 times. Or if I look in the other direction here, I have 26 once, 26 a second time, 26 a third time, 26 a fourth time, etc., etc. There will be 26 up and down, and that will happen 12 times. So there'll be 12 26s. Okay, so now this is a lot to be counting. This is a lot to be drawing. So let's sort of break this up a little bit more. So turn to the second page of that worksheet. And that is where you have this picture. So now what I've done is I've taken my 26 by 12 and I have made some of the lines bold. And what I did is I made each of those lines, the bold lines, after 10 boxes. So if you count how many are here, that's 10 boxes, and then another 10 boxes, and then the last 6 boxes. So there's my 26. Then I have 10 boxes across the top here, and then 2 more, and that's my 12. So now I've broken this up into hopefully something that's going to be a lot easier for us to figure out. So this top box here is actually a 10 by 10 box. This is a 10 by 10 box. Okay, this is a 6 by 10 box. Coming over here, this is a 2 by 10 box. This is another 2 by 10 box. And then this is a 2 by 6 box. Now, just glancing at that, those are very easy, quick multiplications that we can do. So if you look at the picture below that, okay, so I broke it down. So this would be something that you would more likely draw on your paper. Instead of drawing all of those little teeny boxes, so 26 times 12, maybe break it up as you go. So now I have my 10 times 10, my 10 times 10, my 10 by 6, my 10 by 2, my 2 by 10, and my 2 by 6. So those are nice, quick, easy multiplications to do. 10 by 10 is 100, 10 by 10 is 100, 10 by 6 is 60, 2 by 10 is 20, 2 by 10 is another 20, 2 by 6 is 12, and now I have to add these up. Well, this isn't that bad to add up. Now I have 100 plus 100, that gives me 200, plus 60 is 260, plus 20 is 280, plus another 20 is 300, and then another 12, so I have 312. So I'm glad I didn't count up 312 boxes just for the sake of time. But that doesn't mean that the area model is then too difficult or too long for something like 12 times 26. So instead of drawing all those little boxes, we're going to break it up by the place value. So we're going to break it up into tens. And you might find as you work through this that you might decide to break this up a little differently. You're going to sort of get what's comfortable for you. I look for tens, I look for hundreds, and I look for ones. So that's sort of how I choose to break it up. So now let's talk about the algorithm that we would use, the standard algorithm. If you weren't going to use an area model, if you weren't going to use a model, you were just going to do multiplication with the traditional algorithm. An algorithm is just sort of the big fancy word in math for the series of steps that you would take. Okay, so a lot of you would say, oh, well, 12 times 26, you would write the 26 and you would multiply by the 12, and then you would work through this and you would say, oh, well, 2 times 6 is 12, and you would write that here, okay, and then you would do 2 times 2 is 4, and you're going to write that here. I'm writing this stuff in the middle just to show you where we're going. Then you would skip this space, which we kind of forget to think about why we do that, but it's coming from this idea. This 1 is not just a 1, it's actually a 10. So you're multiplying by 10, so that's kicking it up a place value. But then you're going to do 1 times 6 here, and then you're going to do 1 times 2 here, and then you're going to add all of those together. So now, this part you don't usually write down. When you write it down, it looks something like this. 2 times 6 is 12, and you do some weird carrying thing, right? So it goes up to the top. And then you do the 2 times 2 is 4, and then you add that thing you carried, so that's 5. We somehow forget about why we do that, which we'll talk about in a second. And then you put a 0 here, and sometimes you make it dotted. And then the 1 times 6 is 6, and the 1 times 2 is 2, and then you add those together. So now I end up with... Sorry, I ran out of room. So I have 2, and then 5 plus 6 is 11. So then you carry, and then 1 plus 2 is 3. So you end up at the same place. So you still have the 312. Okay, so this is sort of the traditional algorithm. So you do these 4 little multiplications and you add them together, and where you place them has to do with the place value that you're talking about. So what I mean by that is this is 2 ones times 6 ones, so that's going to stay in the ones place. But when I take that 2 and I multiply it by this 2, it's not actually 2 times 2. It's 2 from here, and this is a 20. And so that's why it gets kicked up to the tens place, because this is 2 times 20 kicked up to the second place. Same thing on the bottom. This is what I talked about with the tens. So the 1 is in the tens place. So when I multiply 10 times 6, it gets kicked over. So this is really 10 times 6. That's why it's been shifted over into the tens place. And then the last spot where you do the 2 and the 1, this is actually 1 10. This is 2 tens. So if I multiply by 10 and then another 10, that kicks it over to the hundreds place. So that's why it gets kicked over. So this is really the 10 times the 20. Now, I know I put a lot more on this page than you would ever write, but I did that because I want to show you how what we just did here is essentially what we did with the rectangle. So if I come over here, I'm just going to recopy that really quickly. So 26 times 12, we did the 2 times 6, so I'm going to hold off on the carrying for a second. So we did 2 times 6, which is 12, and then we did the 2 times 2, which is 4, and the 1 times 6, and the 1 times 2, so we ended up with something like this. Well, if I look in my picture, okay, the 2 times 6 is right here, so that's my first step. Then the second step, we did a 2 times a 2, but that's really 2 times 20, okay? So if I look at this box, if I actually put those together, there's my 2 times 20. Then we did 1 times 6. Well, the 1 was really a 10, so that's 10 times 6. So that's this part of my rectangle. And then the last piece was the 10 times 20, the 1 times 2, which is really the 10 times 20. And if I look at my picture again, that is this section. So what we did was we did several little multiplications and then we added them together, which is exactly what we did with the rectangle. Now, one of the nice things about the rectangles is that with the rectangle, I get to choose how to break it up. So for example, I chose to do these two rectangles separately. So I did a 10 times 10 and a 10 times 10 instead of a 10 times 20. Either way works, you end up at the same place, but I had the flexibility to break it up into some smaller multiplications of my choice. Whereas if I use the algorithm, I don't get to choose, right? It automatically breaks that rectangle up for me. But again, you do a couple small 3, 4, 5, 6 little multiplications and then you add them together. And that's exactly what we did with our rectangle, with our area model. We broke it up into, in this case, I broke it up into 6 little multiplications. We did 6 little simple multiplications and then we added them together. So it's not that different from the traditional algorithm. So especially for those of you who are comfortable with the traditional algorithm, with the steps, okay, with what I have written over here, this type of thing, start to draw connections between that and the area model, okay? They're the same. The little multiplications inside of your algorithm are the same little multiplications that you can do inside of your area model. Okay, so then let's talk about fractions. Let's talk about some mixed numbers in particular. So these are fractions greater than 1. We've already talked a lot about doing fractions less than 1. So if you look at, again, at the visual representations of multiplication, those have some examples of doing multiplications with 2 numbers that are less than 1. And you're actually going to get a little practice in here as well. So this, I find more helpful, the idea of breaking it apart if you have mixed numbers. Okay, so here's the setup. So now I have 1 2/3 times 2 3/4. So again, if you notice with the bold, so here's my 1 2/3. Okay, so this right here is my 1. That's my whole, so my area of 1. So then going across the top, I have 1, 2, and then 3/4. So there's my 2 3/4. Okay. So I continued these. So if you notice over here, I went all the way over here and I kept these dashed. They're actually outside of my multiplication area, but they help me keep track of how large some of those pieces are. So you might find that you don't need to put those on the end. I personally like to keep them. Okay, so now I have a rectangle that's 1 2/3 by 2 3/4. Or let's think of this as repeated multiplication. So if I think of this as repeated multiplication, here is 1 2/3 one time. Here's 1 2/3 again. And here's 3/4 of 1 2/3. So I drew the purple rectangle, that is 1 2/3. So if I wanted 3/4 of that, then I'm going to break that up into 4 equal parts. 1, 2, 3, 4. And then I'm going to take 3 of those parts. So I'm going to take all 3 of these. So that's why my bold line ended up where it was. So here is 1 2/3. Here's a second 1 2/3, and then here is 3/4 of 1 2/3. Or I can think of this as 2 3/4 added 1 2/3 times. So here is 2 3/4 one time. Here is 2/3 of 2 3/4. Okay, so again, if I had drawn it all the way down here, that would have given me my 2 3/4. Then I split it here and here to give me 3 equal parts, and then I took 2 of those parts. So this is 2 3/4 one time. So here's 2 3/4 one time, and then here's 2/3 of 2 3/4. Okay, so let's actually find the area of this rectangle. So I have my 1 2/3 by 2 3/4. So the multiplication is going to be the area of that rectangle. So looking at my bold, I know that this is actually 1 by 1. So this has an area of 1. This one also has an area of 1. And now I'm going to play a little bit with moving some of these pieces around so it's easier for me to see. So I did this before on one of the other pages. So I'm going to take this block right here, okay, which actually turns out to be a third, and I'm going to move it here to fill in this space, so that now I have another 1 right there. And then I'm going to come up here, and I am going to take 3 pieces. So let's take these 3, and I'm going to move them over here, right here. And so now I have another 1. Okay, and then what I have left is I have this piece, this piece, this piece, this piece, this piece, this piece, and this piece. Okay, so looking at this, I have 1, 2, 3, 4 holes. And looking at these little pieces, I have 1, 2, 3, 4, 5, 6, 7 of them. 7 pieces when there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces in the hole. Or if it's too messy down there to count, come up to one of the holes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's one way to do it. So 1 2/3 times 2 3/4 is 4 7/12. Now, you also could just count the number of twelfths inside of the original rectangle, and that would totally be fine. That would be an improper form, but that is no problem at all. So if you did want to do that, sorry, my picture's a little bit messy, but looking inside the bold lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55. So you could also have said that the answer was 55 pieces when there are 12 pieces in the hole. And that would have been fine too. That is still the area of the rectangle. So let's talk about the traditional algorithm here. Now the traditional algorithm for some of you doesn't seem so obvious or so traditional when we are talking about mixed numbers, but it would look something like this. So you would take the 2 3/4 and you would think about them as separate columns, and then you would take the 1 2/3 and you would multiply them. So in decimal form, each column is a new place value. Here, it's the same thing, except for the column that is less than a whole number is the fraction part. Okay, so if I were going to go ahead and do the traditional algorithm, I would start with 2/3 times 3/4. Then I would put that over here, and then I would have 2 times 2/3. Okay, and then I would do the 1 times 3/4, and then 1 times 2. And now in this case, I'm not thinking of these as specific place values, and this is where for some of us it's going to get a little bit confusing. What we're doing is we're not lining these up, we're actually just adding all of these together. So in some respects, it might make more sense to look at this as 2 times 2/3 plus 2/3 times 3/4 plus 1 times 2 plus 1 times 3/4. Okay, so the traditional algorithm might look funny in this particular case. So instead of the traditional algorithm, let's think of this sort of like the distributive property. So in an algebra class, you probably called this foiling. So when we break this up, let's think of this as 1 plus 2/3 times 2 plus 3/4. And so now I'm going to distribute. So when I distribute, I know that every number inside of each parentheses has to hit every other number. So I know that the 1 has got to multiply by the 2, and the 1 has to multiply the 3/4. The 2/3 multiplies the 2, and the 2/3 multiplies the 3/4. So there's my 1 times 2 plus 1 times 3/4 plus 2/3 times 2 plus 2/3 times 3/4, and then I have to add all those up. Well, the whole number parts are not at all a problem to add up, but it gets a little bit ugly when I have to start adding up the fractions. And not ugly like we can't handle it, but not near as nice as if we had just used the area model to begin with. Because if you notice, again, if I look at these little breakdowns, 1 times 2, well, that's this rectangle right here. Okay, I would have done that anyways. 1 times 3/4, that's this rectangle here. 2/3 times 2, that's this rectangle. And 2/3 times 3/4, that's this rectangle. And then we're adding them all together. So the area model not only perfectly models this idea of the distributive property or foiling, but it helps us keep track of it, right? If you think about using a rectangle, it's very unlikely, or maybe less likely, that you would mess up one of these breakdowns, right? And again, it gives us more flexibility. We can break it down in lots of different ways. We have a lot more options in how we choose to break it down. So again, the area model is going to parallel the distributive property, which we sometimes talk about as kind of the break apart method. And the reason we think about it as the break apart method is because we've broken apart our numbers. We've taken 1 2/3 and we've broken it into 1 plus 2/3. We take 2 3/4, we've broken it into 2 plus 3/4. So sometimes this is referred to more as sort of the break apart method. We're breaking apart those numbers, which again parallels perfectly with our area model. What are we doing? We're finding the area of the larger rectangle by breaking it apart into smaller rectangles. So another example with decimals. So now we're looking at page 4 on the worksheet. So this is the drawing that's set up there. So now this is an excellent opportunity to use some graph paper. The other one is as well, but this one in particular, because you want to have tenths broken up. In other words, you want each of your little boxes to represent a tenth. So really what we're doing here is we're doing a 10 by 10 grid. So these are little 10 by 10 grids within a bigger problem. So again, let's see 1 4/10. So here's my 1. Notice I have 10 boxes there. So that's 10 tenths, which is 1. And then another 4/10 stuck here. And then I have 1, 2, 3, and 2/10 across the top. So now I'm trying to figure out what this looks like. So if I think of this in terms of repeated addition, so this here is 1 4/10. Here's a second 1 4/10. Here's a third 1 4/10. And here's 2/10 of 1 4/10. Or if I want to think about it as 3 2/10, 1 1/4 times, this is 1, 2, 3 2/10, right? Remember in your 10 by 10 grid, every column or row represents a tenth, right? So here's 3 2/10, and then here is 4/10 of 3 2/10. So now you'll notice this time, for the sake of space, I did not include all 10 of the rows down below there, or even all 10 of the rows columns over to the side, but you could. And if you're using graph paper, you have a lot of wiggle room on both sides. So again, repeated addition allows us to, or helps us, set up these rectangles. So now let's actually figure out what the area is. So I have my 1 4/10 by my 3 2/10, and now because of the way I did the bold lines, okay, it's not too bad for me to figure out the area. So this is a 10 by 10 grid. So 10 by 10, that's going to give me 1. And then I have another 10 by 10 grid, so there's another one. I have another 10 by 10 grid. So that's another one. Now, how you choose to count up the rest of it, there's lots of ways to do it. So one way is to think of, well, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 tenths. So let's keep track of this. So I have 3, and then I have 14 tenths, which you don't have to write in fraction form, but that's just how I'm going to keep track of it right now. And then I have the last little bit over to the side there where I need to figure out what this is. So I have 1, 2, 3, 4, 5, 6, 7, 8 hundredths. So these are sort of my three things. So I tend to, and this is a little bit ugly for some of you, but I tend to write it like this. So I say that this is 3 wholes, and then it's 14 tenths, and then it's 8 hundredths. Now, I know I can't write an answer like that, but that helps me keep track of it. I know then that I'm going to carry. So I have these 10 tenths that are going to get bumped over. So I'm going to end up with 4 wholes, 4 tenths, and 8 hundredths. Now, if you want to not write this part here, go for it. If that symbol, if that writing it down like that is confusing to you, then just ignore it. That's fine. Well, all you need to be able to do is you need to be able to add the 3 plus the 14 tenths plus the 8 hundredths. And if you want to do that in decimal form or fraction form, your choice, doesn't matter. That's just one way to count up the boxes, the area. Another way to do it is to move them around. That's what I did on several of the other ones, which wouldn't be too bad. So here's 4 tenths. So I match them up with another 4 tenths. So that's going to be 8 tenths. So then I just need 2 more tenths. So I'm going to come up here and grab these. So then I know that if I put these red ones together, they equal another 1. So there's my 1, 2, 3, 4. And then I have 1, 2, 3, 4 tenths left, and then I still have my 8 hundredths left. Excuse me, so that would still get me to the 4 and 48 hundredths. So that would be fine too. So let's compare it to the distributive property or the break apart method. So this is actually 1 plus 4 tenths, and this is 3 plus 2 tenths. So distributive property would mean I would need to do 1 times 3, and add that to 1 times 2 tenths, and add that to 4 tenths times 3, and add that to 4 tenths times 2 tenths. And if we look back at our rectangle, right, all of those are there. 1 by 3, that's this particular rectangle. That rectangle is 1 by 3, so there's 1 times 3, so that's your area of 3. And then the 1 by 2 tenths, that's coming up over here. So this is 1 by 2 tenths. So that's that. Little multiplication, 4 tenths by 3, that's going to be this skinnier rectangle down below. Is 4 tenths times 3. And then the 4 tenths times 2 tenths, that is what's hanging out over here. So again, the distributive property parallels perfectly with the area model. The only difference is that the distributive property is much more restrictive, right? You can only have, in this case, you are only going to be able to represent the larger rectangle broken up into 4 very specific rectangles. Whereas when I did it, I broke it up into more. It was easier for me to do it that way. The advantage of the area model is that you can sort of break it up however you want. Once you have the rectangle set up, then you decide how to count it and figure out what's inside. Looking at the traditional algorithm, we have the 3 and 2 tenths, and we're going to multiply that by the 1 and 4 tenths. So again, following the same pattern, we're doing 4 times 2, which is 8. We're doing 3 times 4, which is 12. And then we do this place value holding thing, and then 1 times 2 is 2, and 1 times 3 is 3, and then we have to add those up, and we get 4, 4, 8, and then the most common mistake that we see is we don't know where to put that decimal point, right? So there's certain rules of where to put it when you add and when you subtract, and it's different from when you multiply. And so if you don't think about what's happening and you're just trying to memorize rules, which I'm very against in this course, then there are a lot of mistakes that can be made here. Okay, so the area model, you don't have to worry about where the decimal point goes. It takes care of it for you. Okay, so it's another reason I like the area model. But in some situations, the area model is not going to make sense for decimals because there are going to be too many place values, or those numbers are going to be too small. So this is a situation where estimating can be extremely helpful. The estimation can help us figure out where that decimal point should go. So if I'm going to estimate 3 and 2 tenths times 1 and 4 tenths, I'm going to make that a 3 and a 1. So that's 3 times 1. So my estimate is 3. So then my challenge is, where do I put the decimal point to make these two numbers as close to each other as possible? How can I make 3 and that number as close as possible? Well, if I tried it over here, 3 is nowhere close to 448, so that's not going to work. If I put it here, 3 is nowhere close to 44.8. If I put it here, 3 is pretty close to 4.48, so that might be the one I want, but let's keep going. If I put it here, I have 0.448. So 3 is actually closer to 4.4 than it is to 0.4, so it's not going to go here. So estimating with just a little bit of thinking is going to help us figure out where that decimal point goes, or it's going to check. So if you think you know where it goes, put it there and then make sure it matches with your estimate. So this is a situation where estimating can be extremely helpful in catching errors of where to put that decimal point, because I guarantee it, this is a very, very common mistake that a lot of you make. Okay? You're not sure where to put that decimal point, or you just put it in the wrong place. Okay, so now let's take 4 5/10 and multiply that by 3 1/10. So this time I'm not going to use a drawing. I'm going to explicitly show you the break apart method. So if you look at page 5, this is where it's written out. Okay, so I'm just sort of talking through that thing at the top, all those steps at the top. So one way to interpret this is 4.5 added together 3.1 times. And so breaking the 3.1 apart, I can think of this as the 4.5 added 3 times and then added another 1/10 of a time. So I really want you to be able to understand that step, how we got from this line to this line. Because if you get that, if you really get it, then this break apart method is just that step over and over and over to turn it into several little straightforward, easier multiplications. Okay, so 4 5/10 added together 3 1/10 times is the same as adding 4 5/10 3 times and then adding 4 5/10 1/10 of a time. So then we're going to break that down again. So now I'm going to take 4 5/10 added 3 times and I'm going to break it into this part right here. So 4 added 3 times and then my half added 3 times. Same step from before. Then I'm going to take my 4 5/10 added 1/10 of a time. I'm going to break it up into this part. So now that's 4 added 1/10 of a time and then 0.5 added 1/10 of a time. I really want you to be able to intellectually understand those breakdowns. Okay, why that's happening. If I need to add 4 1/2 a certain number of times, I can add the 4 that many times, and then I can add the half that many times and put them together. All right. If I have to reimburse you $20.05, and I have to reimburse you that for the 5 times that you did that this week, I could give you a $20 bill and then a nickel, and then a $20 bill and a nickel, and a $20 bill and a nickel, as many times as I needed to. Or I could give you all the 20s first, and then I could give you all the nickels after that. That's the same idea as what's happening here. So now what I've done is I've broken this into 4 smaller multiplications. 4 added 3 times is the same as 4 times 3. A half added 3 times is the same as a half times 3. 4 added 1/10 of a time is the same as 4 times 1/10. And then 0.5 added 1/10 of a time is the same as 0.5 times 1/10. So now I've broken it into these 4 smaller multiplications, each of which hopefully we're comfortable with now. So my 4 times 3 becomes 12. My a half times 3 becomes 1 1/2 or 1.5. 4 times 1/10 becomes 4/10, and then 5/10 times 1/10 becomes 5/100. So if this part right here you're not really confident about, go back and look at the estimating video. We did several examples of multiplying decimals that only had one non-zero place value. So in other words, had the 5 and the 1. Okay, to help you figure out where that goes. And then I'm going to add those up. 12 plus 1.5 gives me 13.5, plus 4/10 gives me the 13.9, and then the 5/100ths, there's my 13 and 95/100ths. Okay, just to repeat this process, doing it in the other way, okay, this can be 4.5 added 3.1 times. So that's 4.5 plus 4.5 plus 4.5 plus 1/10 of 4.5. And then I can break that up even more. So here's my 4 and my 0.5, my 4 and my 0.5, my 4, my 0.5. And here is 1/10 of 4 and 1/10 of the 0.5. So again, this is breaking it up. So if I'm adding 4.5 3 and 1/10 times, there's my 4.5 plus 4.5 plus 4.5. So that's 3 times. Well, then I need another 1/10 of a time. So I'm going to tag that on the end. Then in the next step, I broke it up even more. And then it's addition, so I'm going to rearrange it. So don't make these two lines look confusing. All right, follow it. This 4, this 4, this 4. And then I put the 0.5, the 0.5, and the 0.5. And then over here, I did these little multiplications. So 1/10 times 4 gives me 4/10. And then 1/10 times 5/10 gives me 5/100ths. And now I can just go ahead and add these. Okay, so now I can take the 4 plus 4 plus 4, that's 12. That's a 1, so then that's 13. That's 9/10, so I'm at 13 and 9/10 and 5/100ths. So there's my 13, 9/10 and 5/100ths. Using the idea of repeated addition combined with this idea of breaking these numbers apart is how we can think through some of these multiplications without getting tied to or stuck with the algorithms. I really want you to understand what's happening, not just get, oh, if I memorize these steps, I get where I need to go. Okay, so this might be a drawing of something you might do for the 4 and 5/10 times the 3 and 1/10. Okay, so I didn't draw all the little shapes this time, but the idea is still there. So if I look at this, okay, I still have my 4.5 across the top, and I still have my 3 and 1/10 down the side. Okay, but I broke it up. So this section is going to be my 3, and this section is my 1/10. And looking across the top, this first section is my 4, and the second section is my 5/10. And now I have little multiplications on the inside. Right? So this rectangle here is 4 along one side and 3 along the other side. So there's the 4 times 3. 4 on one side, 3 on the other side, so the area is 4 times 3. And then it's the same thing for all of them. So this rectangle here has a 3 along one side and a 5/10 along the other side. So the area of that rectangle is 3 times 5/10. Skinny rectangle at the bottom, one side is 4, one side is 1/10. So this becomes 4 times 1/10. And then this last little rectangle is 1/10 on one side and 5/10 on the other side. So sometimes you might find that using the area model with the rectangle is really just a way to keep track of the more traditional algorithm. It's the 4 little multiplications. Maybe you don't draw this to scale at all, and that's totally fine. Right? You know that you have a 4 and you have the 5/10 along one side, you have a 3 and 1/10 along the other side, and those, just using the place values, will break that up nicely into the 4 different sections. This idea can be extremely helpful if you have a number that has more place values. So you have a number that has 3 place values by a number that has 4 or 5 place values. It will help you keep track of some of those little multiplications. And again, perfectly parallels the traditional algorithm. So just to look at the traditional algorithm, 4 and 5/10 times 3 and 1/10. So the first thing we're going to do, or one of the things we're going to do the 1/10 times the 5/10. So that's what's here, right? So there's your 5. And then the next thing we're going to do is we're going to do the 1 times the 4. So the 1/10 times the 4, and that's here. And then the next thing we're going to do is we're going to do the 3 times the 5. So that's 3 times 5/10. So that's here. And then the last piece, we need to do the 3 times the 4. And that's 3 ones times 4 ones. And that's happening here. And then to finish out the problem, you have to do the addition. So in the traditional algorithm, since I did the multiplications over here already, I would just fill these in. And then, again, have to decide where that decimal point goes. Whereas if I use the rectangles, the decimal point never gets lost. Okay, it's already in there. I already know how to line up my numbers. I already know how to add them together, so it's not a problem. If you're using the traditional algorithm, just to remind you, do some estimating. 4.5 times 3 1/10, that's between 3 times 4 and 3 times 5. So you know your answer needs to be between 12 and 15. So the only place to put the decimal point to get your answer between 12 and 15 would be to put it here. So there's your 13 95/100. Okay, last example on this worksheet, so turn to page 6. I know, so for some of you, this is a lot. So this is our last example to go through. So it's going to be another fraction. So I have 3 1/3 times 4 2/5. So I'm going through the break apart method. That's on page 6. So one way to interpret this multiplication is 3 1/3 added 4 2/5 times. So here's 1, 2, 3, 4, 3 1/3, and then 2/5 of 3 1/3. Then I'm going to break that apart. So every 3 1/3 is going to get broken into 3 plus 1/3, 3 plus 1/3, 3 plus 1/3, 3 plus 1/3. And then in this last part, if I want 2/5 of 3 1/3, I can find 2/5 of 3 and add that to 2/5 of 1/3. So if I want 2/5 of a large number, I can take 2/5 of each part of that number. And so then I'm going to rearrange again. It's addition, so I can do it in any order I want. 7 plus 8 is the same as 8 plus 7. So here I'm going to rearrange. I'm going to take the 3's, and I'm going to stick them next to each other. I'm going to take the 3rds, and I'm going to stick them next to each other. And then I'm just going to rewrite 3 plus 3 plus 3 plus 3 as 3 times 4. And then the same with the 3rds is the same as 1/3 times 4. And then I kept the 2/5 times 3 and the 2/5 times 1/3. And then I can do these little multiplications. So 3 times 4 is 12. 1/3 times 4 is 4/3. 2/5 times 3, so that's 2/5 3 times, so that's 6/5. And then 2/5 times 1/3. This last part, for me, I like to draw it out. So I'm going to take 1/3, which might look something like this. And then I want 2/5 of that, so I'm going to break it into 5 equal parts. And I'm going to take 2 of those. And so then I'm going to count. So if I describe that, I have 2 pieces that are shaded, and then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 in the hole. So there's my 2/15. 2 were shaded, 15 in the hole. And then to add these, I would have to find my common denominator and put them together. Now, if I do this using an area model, then it looks something like this. So here is my 1, 2, 3, and 1/3. And then coming down the side is my 1, 2, 3, 4, and 2/5. Or again, if I look at this as 4 2/5 one time, 4 2/5 the second time, 4 2/5 a third time, and then 1/3 of 4 2/5. So again, the idea of repeated addition can get me to my rectangle. Okay, so once we're there, how do we figure out what this area is? Well, first, let's try to understand this scale, because as you start to draw these, you're going to have to do this on your own, figure out what this scale is. So for me, the bold lines, most of the bold lines, are representing an area of 1. So this rectangle here is going to be an area of 1, which means coming from the top, it's been split into thirds, and coming from the side, it's been split into fifths. Hopefully you see where that came from. If not, let's figure it out. So the third comes from the third, and the fifths come from the fifths. Okay, so that's how I split it that way. So if I want to find the area here, then I'm just going to start counting. This is an area of 1, this is an area of 1, of 1, of 1, of 1, of 1. I have a bunch of areas of 1, which is no surprise because I have a number that's bigger than 3 times a number that's bigger than 4. And then again, we can start playing. So I like to move things around, and this one is not a bad one to move around. I can take all these, and I can stick them here, and I can take these, and I can stick them here. And that gives me another one right there. I put those 3 together. So I'm going to write a crooked one just to make sure I know what's going on. Then if I come down to the bottom here, I can take this chunk, and I can put it here. And then I can take half of that right there and put it down here. And that gives me another one going through all those. And now I'm just going to count up these extra pieces. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 extra pieces. So I know that it's going to end with a 10 in the numerator. So let's finish that off. There's 10 pieces when there are how many in a whole? Well, if I go to count those, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 in a whole. Or if you feel a little bit safer and you want to go and count one of the holes that is shaded, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 15. So then the whole number out front, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Or if I think about the distributive property, I can do that as well. So this is 3 plus 1/3 times 4 plus 2/5. So then I end up with 3 times 4 plus 3 times 2/5 plus 1/3 times 4 plus 1/3 times 2/5. Which are all little multiplications that I can do, and then I'll have to find a common denominator to be able to add them together. But just to show you, this shows up perfectly inside of your drawing. So here's your 3 times 4. It did all the whole number part together. And then you want the 3 times 2/5. So the 3 times 2/5 is going to be down here. The 1/3 times 4, that's what's happening here. And then last but not least, the 1/3 times the 2/5, and that's here. So the distributive property, or the break apart method, again, parallels nicely with the rectangle. So hopefully you've noticed after we've done several of these examples that the idea of repeated addition, a repeated addition with the idea of breaking the numbers apart, parallels perfectly with the distributive property, which is breaking numbers apart, parallels perfectly with the rectangles and drawing out those rectangles. And I hope that as you go through more of these problems, that you start to feel more comfortable with these rectangles, some of which you're going to need to draw out every single one and every single decimal and every single bit of a fraction. And then as the numbers get a little bit bigger or have a few more place values to them, you can start to break them down into chunks. And so you're just going to have a rectangle that's broken into 4 parts or 6 parts or 9 parts. And the rectangle is going to help you keep track of all of the little multiplications that have to happen before you can add them together.